Hey, Calculus, Mr. Florio. We're going to do a couple more examples from 5.3 definite integrals. What we said last time is that if I want to find the area, as long as my function is continuous and non-negative on the closed interval from a to b, then the area is just a definite integral of that function from a to b. So sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. So the definite integral of the function f of x equals 4 from x equals 1 to x equals 3, they're asking what is the area under this function between x equals 1 and x equals 3 and the x-axis. So let's just draw that. All right, so the function f of x equals 4 is just a horizontal line at 4. Now, I want to know the area of that function between x equals 1 and x equals 3. So the area between that function, the x-axis, and the vertical lines x equals 1 and x equals 3 is this region right here. Now it says use geometrical formulas to find this area out, and that should be pretty straightforward. This is just a rectangle. The base looks like it's 2. The height is 4. So the area is going to be base times height, which is 8. So the definite integral of the function 4 from 1 to 3 is 8. So the strategy is to draw the graph and see if you can find a geometric formula that'll find that the area of that figure for us. So here I have the function x plus 2 from 0 to 3. So let's see. X plus 2 has a y-intercept of 2. And the slope is 1. That's just a line. So it's going to look like this. And I want to find this between x equals 0 and 1, 2, 3. So between 0 and 3, the function and the x-axis, that's this region right here. And that's a trapezoid. Now, if I want to find the area, I could use a trapezoid formula, or I could break this up into a square and a rectangle and a triangle. So if I break this up into a rectangle and a triangle, this has a base of 3 and a height of 2. 3 times 2 is 6. So the area of that region is 6. This has a base of 3. The height of this triangle, let's see, when x equals 3, 3 plus 2 is 5. So this is going to be 5. So the height of this triangle, let's see, subtract the 2, so this is going to be a height of 3. So the area of this, let's see, 1/2 base times height. 1/2, the base is 3, the height is 3. So that's just going to be 9/2, or 4.5. So if I add 9/2 and 6 together, let's see, that's 12/2 plus 9/2. I think that's 21/2. So we get 21/2 here. If I use the formula for a trapezoid, the area of a trapezoid is 1/2 base 1 plus base 2 times height. So you take the average of the bases and multiply that by the height. So the bases here are 2 and 5. So it's going to be 1/2 2 plus 5 times the height. The height is 3. So that's 7 times 3 is 21. So that's 21 divided by 2. So we get the same answer, whether you use either formula. And if you recognize what this this function is, it's that'd be impressive. It's a semicircle with radius 2, and we're going from -2 to 2. And so it's just going to look like this. And that's at +2. So what's the area of this? That's going to be straightforward too. The area of a semicircle is just pi r squared, and we want a half a circle, so we're going to divide that by 2, which is going to be pi times the radius is 2. which is going to be 4 pi over 2 or 2 pi. So that's it. If you want to find the area, if you want to evaluate the definite integral, if it's a nice function that gives you geometric shapes, we can use our geometry formulas to find the area, no problem. All right. Definitions of two special definite integrals is if f is defined at x equals a, then we define the integral from a to a of a function 0. This question, or this particular property, is one of those ones that stick out to me just because I got a question wrong on a test that was really easy, but I did it the hard way and made a mistake and had to pay the price. So if I want to use property 1 to answer this first question, what's the area under the curve sine x from pi to pi? The sine function is just your wave. We're going from 0 to pi, or excuse me, we're going from pi to pi. What's the area that's in this region that it starts at pi and ends at pi? Well, that rectangle, that region right here, has no width. It's just going to be 0. There is no area there to look at. We're just finding the area at a specific point. You need a width. You need the interval to be bigger than 0. And that's why that's just going to be 0. So it makes sense that if your upper and lower bounds are the same, there is no area if you don't have any width. So if you like the area of a rectangle with a base of 0, 0 times anything is going to give you 0. Anyways, the second property is that if the function's integrable on that closed interval, then we can define the integral from a to b of f of x to be negative the integral from b to a of f of x. So if we switch the upper and lower limits, that's no problem, but that's just going to cause our sign to be negative. So if I want the area from 0 to 3 of x plus 2, that's the same thing as flipping this from 3 to 0 to 0 to 3 and just making sure we add that negative sign. So that's just a property that we have, and this is going to be pretty straightforward. We answered this piece already. The integral from 0 to 3 of x plus 2 we said was 21 over 2. So it's just going to be 21 over 2, but we have that negative there. And that's just a special property that we have. One other theorem that it's one of those ones when I guess when you see it, it makes sense. The additive interval property doesn't sound too intuitive, but what they're saying, if f is integrable on 3 closed intervals determined by a, b, and c, then the integral of f of x from a to b is the same thing as taking the integral from a to c plus c to b. Drawing that out, I think, is a little bit easier. So say I have some interval a to b, for example, and say c is somewhere in the middle. Here's my function. If I want to find the area from a to b, that would be this region right here. So if I want to find that, that would be the same thing as taking the area from a to c and adding that with the area from c to b. So if I take the red area and the green area, add it up, it gives me the entire blue area. That makes sense when it's drawn out. Maybe it's a little more confusing in the theorem box, but that's all that it's saying. Is if I have the integral from a whole interval, I can break it up into 2 pieces and just add those 2 pieces together. Where that's going to be helpful is in this example right here. If I wanted to find the area under the absolute value of x from -1 to 1, what does that look like? The absolute value of x looks like this. And I want to find the area between the x-axis, that function, and -1 and +1. So I'm really just looking for this area right here. And so what I can do here is rewrite this as, let's go blue. This is just the integral. I'm going to go from -1 to 0. This function here is -x. and add that to the integral from 0 to 1, the definite integral from 0 to 1 of the function x. So this would be the absolute value of x. It's a piecewise function, if you remember the actual definition of it. And when you plug in negative values, then you put another negative on it. That's what makes it positive. And when you have positive values, it just stays regular x. You don't really do anything to it. So if I can just add up these two integrals separately, we'll be all set. So the first half is going to be this green area right here. That area is just going to be 1/2 base times height. The base is 1, the height is 1. So the area of that triangle is going to be 1/2. And we're going to do the same thing with the other triangle, and I think it's going to be the same thing. The base is 1, the height is 1, so that's going to be 1/2 base times height, which is going to be 1/2. So when we add these together, the area of the entire thing is 1. So to find this antiderivative, excuse me, not this antiderivative, this definite integral, it's just going to be two separate integrals where both areas are 1/2, and when we add those together, we get that the area is 1. So those are some quick examples. These properties of definite integrals right here are the same ones that we had before. If I have some constant that's multiplying my function, I could always factor that constant out. That was true for indefinite integrals. It's also true for definite integrals. And if I'm taking the integral of a sum, that's the same thing as taking a sum of two different integrals. So I can just take the sum of f. You can think of it as distributing the sum of f of x and g of x. And that'll be fine whether you're adding or subtracting. So using that property, this is the last example. Yep. Let's evaluate the definite integral of the function negative x squared plus 4x minus 3 dx using each of the following values. So we know the integral from 1 to 3 of x squared is 26/3. The integral of the function x from 1 to 3 is 4, and the integral from 1 to 3 of the function, you can think of this as 1 dx is 2. How is that going to help us here? It's actually going to help us a lot. So I want to evaluate this. So using property 2, I'm just going to distribute the sum and take the sum of negative x squared from 1 to 3 plus the sum, I keep saying the sum, the definite integral from 1 to 3 of the function 4x, and the sum from 1 to 3 of the function negative 3 dx. And I almost can use these three things to directly substitute in, but this has got a negative in front of it, this has got a 4, and that should be a 1, this is a negative 3. So I'm going to use this property up here, number 1, that I could factor out constants. So here I can factor out that negative 1, think of that as a negative 1, so it's negative integral from 1 to 3 of x squared dx. I can factor out the 4 times the integral from 1 to 3 of x dx, and I could factor out the negative 3, and I get the integral from 1 to 3 of dx. You could think of it as 1 if you want, but I'm going to take it out. And now we can directly substitute in. This right here we know is 26/3. That was given to us. We didn't have to figure that out. That was nice. So I got negative 26/3 plus 4 times the integral of the function from 1 to 3 of x we know is 4. So I'm going to plug that in right here. This thing right here is just 4. And then we have minus 3 times the integral of dx is just 2. And that's pretty much it. Just multiply it all out. Combine like terms. We have negative 26/3 plus 16 minus 3 times 2 is 6. So that's negative 26/3 plus 10. 10 is the same thing as 30 over 3. So 30 minus 26, that's going to be 4/3. So that's what we get. We evaluate this integral. It's 1 1/3 or 4/3, and that's it. So the algebra in this section isn't anywhere as intense as it was in the last section, but there's just a lot of notation going on. The actual calculation is going to be a lot from area formulas from geometry, and maybe just this little plugging in numbers using the property list. All right, that's all.